Ryan and Aaron, who are sitting up front there. Can people hear me just fine at the back? Loud enough? Okay, thank you. Great. So imagine for a moment that you're not a PL researcher, but you're a sysadmin at a lean startup, and it's your job to sort of get your sort of website up and running. So how might you go about this? So you log into your machine, and you install the Apache web server. You edit the default site configuration. You restart the web configuration, and then you get it wrong the first time. So you edit the configuration some more, you hit restart it again. This time you get it right. You probably want to secure the server in some way. You firewall, perhaps using IP tables. That need to, well, perhaps what you might want to do is set up some sort of backup job that runs on a daily schedule. Okay, so your web server is up and running, everything's going well. In fact, things are going really well. You're getting a lot of hits, a lot of traffic, and so now what you need to do is get many more replicas up and running so that you can handle the volume of traffic that you're getting. All right, so let's do that. Now, what were those commands again that we typed? So hopefully, what you did, perhaps if you were anticipating this, you may have even written down a little shell script. New servers. Now imagine that you had to do this at scale. Imagine that you had hundreds, maybe even thousands under your control, and you had to bring up, Mac desktops and Windows workstations, web servers, and so on and so forth. Manually editing things on the command line and quickly become unscalable. So software bugs, a lot of outages these days are caused not by bugs in software, but so the New York Stock Exchange went down a configuration error. There was a CU, and perhaps most seriously, for 2.5 hours, the problem, people started calling, said that the advent of it's become a problem that a lot of people have. Advent of it's become a problem that a lot of people have. Of configuration management tools, there's a whole bunch more. Puppet works as this. You write your configurations in a domain-specific language called Puppet. The machines in your works as this. You write your configurations in a domain-specific language called Puppet. The machines in your enterprise that pulls down the that smallest possible. So all we're doing here, many times on machines. What you can also do now, you've probably that stuff right. So now the tree necessary to create the file, you can add this attribute called authorized keys. That file exists. Perhaps if someone has locally customized it, really, really common. And so Puppet has this higher level abstraction. This is just, so I've just shown you two different resource types here. There's declarative specification language that you can use to sort of level system commands involved, right? Creating the file, changing might want from a configuration language such as this. You'll get your configuration wrong. So to return to our first example, what running and working correctly, you might, well, configuration application, I'll sometimes use the word manifest. The same state as the test machine. Okay. The way Puppet works is that sure that the state of the machine hasn't simply reapplied to a machine that's already properties. If you just sort of look through the Puppet okay. So the question is it really what goes wrong? Okay, so let's sort of configuration. Here we're creating a user account called Carol. It seems perfectly fine. Doesn't seem to be anything wrong with this configuration, but in any order. So this configuration, the file resource before the user account, adding that line, which creates an explicit dependency that Puppet is able to actually, you know, operating systems. The home directory of Carol may not okay, so here's so this seems like a perfectly reasonable configuration. If you look at the dependencies of Go language, it just does. But back and forth between having both packages installed and simply totally order all resources. Imagine that we wrote down, so Puppet has development environments. So we have, Make, M4, and GCC. Processor. So now, if one developer so keeping is a way to make Puppet management of a non-idempotent manifest. So the first, the second resource says file2 should be deleted. File2 is absent. Okay, so about how we may go about verifying the things that's going to make this hard. So first off, so we've seen that are built into Puppet. There's a bunch of OS specific and Windows specific things too. Two keeps growing like any real world configuration language. They sort of keep they also remove features now and then, which is interesting. I don't want to sort of as a language which provides lots of abstractions we can transcribe the graph, and we can then start reasoning about apart from checking determinism or idempotence. For the rest of the talk is talk about checking little straw man argument here. So testing is in actually try to test all possible installation orders. So it makes sense to try some kind of static analysis. Okay, so remember, the problem here is that there's actually modeling these, well, actually writing down the may interact with each other would be intractable. So what we do is we do model imperative file system manipulating programs. So I want to give you a quick models look like. So for example, for the all we have is a simple file resource. We translate it into a little, check to see if the file exists, we remove it if it does, and then we with the contents written. If the there, we turn it into that program instead, which does it already exists. It sort of leaves it alone, and turn it into a longer program that creates the entire directory, create the file. And so basically, there's this sort of model which models very precisely various legal combinations of attributes on each resource. Another resource packages. So what we need to do is query the operating system package manager. So if you have a resource such as package vim ensure, make a call to either repo query on Red Hat or to apt on Debian systems, and we get a list of files, and we essentially turn a package into a repo that creates all the files and directories necessary for the package. What this means is that you can think of a small imperative program that takes as input a file system and an error if the preconditions weren't met. And you can think of the semantics of a graph of resources as a function that takes the file system and produces a set of file systems or error. So it's simply, so to check determinism, we simply need to check possible output file systems as one for all inputs. Really easy to sort of encode this as encoding this relation as a form. So that's what we're going to do. But before we do that, we're going to have sort of three problems. So the formulas that you get are billions of variables, and so some amount of work is necessary to prune these formulas down to a reasonable size. And parts that we use here that I want to talk about. The first thing we're going to do is deal with this sort of, at a high level. Let's say that we have, abstractly the square resource and the circle resource, with no explicit dependency in between them. What we have to do is consider both possible installation orders, but if we can prove that the two resources commute with each other, installation order. So the way this is normally done, as I'm sure a lot of you know, is to sort of calculate the set of locations, which in our case are the directories in the file system that various resources read and write. Right? So essentially, if you have no overlapping writes, the two resources commute. Is true for Puppet 2 because of the way packages work. The semantics of packages is that they create the directory tree to create the files in the package. Packages may write to user bin and so on. So if you just use commutativity check, you'll find that all packages make work. So what we have is, well, we to define a sort of, commutativity check, which essentially looks for, which is creating a directory tree. So essentially, if you have resources with non-overlapping writes, but they may create a subset of the directory tree, then they do commute with. details you have to get right here. For example, they need to actually create, so on and so forth. The details of that are in our paper. Okay, so what this does, so what cut down dramatically the number of paths we need to consider. So the next thing I want to tell you about is sort of the size of the states. So let's say that all we were doing was installing these two packages, Git, which has about 500 files, and this package of icons, which has over 7,000 files. Now, if we did this naively, what we'd wind up doing is sort of tracking the state of files through every state and through all the intermediate states in there. But we don't need to do that, right? Because it's quite unlikely that the icon theme package actually writes and vice versa. So really, checking determinism, different orders of resources are equivalent to each other. So if we have a circle resource and we're trying to prove that they are not equivalent to each other, if we can identify, let's say, in them and show that it commutes with everything else, we can actually remove it entirely from the check without non-determinism check. Okay, and so this is what we do. So just to be clear, if you have this little manifest fragment, and this is an actual bug that we found. This manifest creates a package called Apache file, and it looks fine, but again, you must create that the file must be created after the package because there isn't an explicit dependency. So what our check does is prune out all the files in the Apache package except for that one file that the other resource may interfere with. So this dramatically shrinks the size of the model. So similarly out here, let's say we're creating two user and again creating a file in my home directory. It's going to entirely prune out the user account Ryan, but keep the home directory, but keep my home directory because the SSH keys file may interfere with that home directory. Okay, and so this has to do with finite states. So so we're trying to prove that what we're really trying to do is are or are not equivalent to each other, and bound the domain of file systems. So if we were working with these two programs, is to say that the information is just the paths that appear in. But if you look at these two programs, test to see if A is a directory, and Q prime checks to see if A is an empty directory. That distinguishes these programs is a file system file within the /A directory. So some additional work is necessary to sort of introduce these additional paths at locations where we check, and so on. So in the little bit of time that I have, this thing works. So we have a website where you sort of see, well, what the website has are a bunch of small demos and some larger benchmarks. So here's one of the larger benchmarks in our paper. So you can hit run rehearsal, and this normally takes about 2 seconds to run, but with the network latency, etc., it'll take a little longer. Is that weird? Okay, so what this does is it says, okay, so this manifest happens to be non-deterministic. So it says determinism checking failed. These depend. So the neat thing that you can do here is you can actually copy it as Puppet as a fragment of a Puppet. Paste them in here. You can actually think of it as a sort of a program, as an paste these in here once actually tell me that deterministic. And once it's able to show that the run additional checks, such as checking that the manifest is idempotent. And so there's a bunch of other smaller demos that sort of illustrate the kinds of bugs that the tool finds. Okay. If you look at the graphs on a paper, what you'll find is that the optimizations that I've talked about are really essential. If you don't do them, it sort of doesn't work. The tool very quickly times out on even moderately sized examples, and you can see that what the optimizations are really doing is dramatically cutting down the number of paths under consideration. Let me conclude here. If you I encourage you to check out our paper. You'll find that checking item has barely any overhead beyond checking. Once you've managed to prove that manifest is deterministic, you can assume you're working with a function and not a relation, and that property is much faster. Thanks for questions if you have any.
Hi, I'm Eric Heide from the university. Your paper says that you model other resources as well, in particular services. Is there anything particular modeling them? These are not, I mean, so a service is a running process, right, which is not a, is there anything can you say a few things about how you model?
Yeah, so I audio from models. So it is a model. I miss. So in particular for services, we essentially checks to see that the service file, that the service startup file is present, but it doesn't actually model the running process. So there's certain kinds of bugs that we may not be able to that we may miss here. So you determinism and idempotence bug that involve services running or not running. But if you wanted to sort of extend the tool to catch other kinds of bugs, yeah, you would need a richer model.
Great stuff. So at the beginning of your talk, you mentioned that there's a tension sort of between modularity and determinism, at least of these dependencies.
Mm-hmm.
So your tool is asking users to put in than they might have otherwise. Have you seen the tension between modularity and arise because you have to put in these additional dependencies? Or is it the case that you have to put in just a small number of them and it doesn't really affect the modularity properties that you're worried about initially?
So blindly follow the suggestion, and we're actually working on sort of that we report.
Okay, cool, thanks.